Hi, welcome to a short video for use in calculus to review simplifying some equations or expressions that we will use mainly when you get to implicit differentiation. So this is definitely a video that you would want to watch before doing implicit differentiation in Calc 1. So let's just say that I have the equation, or it is not an identity, so we'll just call it an equation for right now. A cubed plus b cubed equals the sum of a plus b quantity cubed. Now, I am not saying that this is true for all a and b. For example, if you put in a 2 and a 1, that is not necessarily true. However, there are values for a and b that would make this statement true. For example, if a is 0 and b is 1, or vice versa. If they are both allowed to be 0, that is obviously still true. So there are some values for a and b that will make this statement true, but this is not an identity. This is not saying that you can just cube the binomial inside and get a cubed plus b cubed. So what we should do is determine what is that binomial cubed. And so if I actually use either the binomial theorem, Pascal's triangle, or just go off to the side and multiply a plus b times the quantity a plus b, and then get my trinomial, and then multiply that by a plus b again as a quantity, I would come up with this as a result. Again, I could have also used binomial theorem or Pascal's triangle. I will get a cubed. I will have 3a squared b. I will have 3ab squared and b cubed. And if you remember binomial theorem and Pascal's triangle, the coefficients are 1, 3, 3, and 1. That's what I have. And then a is going to count down, so 3, 2, 1, and then no a's. And the b exponents increase, so none, 1, 2, and 3. Okay, so now that I have that, I can see that I can subtract a cubed from both sides. That will leave 0 in that quantity. And I can also subtract b cubed from both sides. So I have 0 equals 3a squared b plus 3ab squared. And what I'm hopeful that you are in good habits of doing also is making sure that you write 0 equals, because it still is an equation, so we still need to keep that the same. I can factor out a 3, and I'm not going to factor out anything else quite yet. I can divide both sides by 3, because 0 divided by 3 is still just going to get me 0. So I'm not really changing anything, any value of these variables. And so I would say this is probably the most simplified that I can get this equation. I could factor, but again, when we go to doing the derivatives, which again, you're on your way to implicit differentiation, I would much rather use something that looks like this than something that looks like the beginning, because it's going to be difficult to solve. So that's the first thing. Okay, and now let's look at the following. So if I have an expression, so something like given, and I'll use y squared is equal to x cubed, simplify the following. And let's say it's going to look ugly for a second here. 12xy minus 6x squared times 3x squared over 2y all over 4y squared. Okay, so this is what I'm starting with, and it definitely looks quite ugly. And I hope you can see that I have a complex fraction, because I have fraction inside of fractions. And so I'm going to try to simplify this first before I get rid of that complex fraction, because I hope you can easily see, for example, that that 2 will divide into that 6. So I have 12xy minus, and that will become 3 times 3, which is 9x to the 4th, because I have x squared times x squared, over y, all over 4y squared. And now I can see that I definitely still have a complex fraction. And please, when you're writing this, help yourself. For example, I can kind of see that this 12xy is over 1, so my numerators within my numerator are aligned, and then any denominators would also be aligned. So it's just easier to see. So I'm going to multiply the top by y. Then that means I have to multiply the bottom by y, because truly I'm just multiplying by a factor of 1. I'm changing the way it appears, but I'm not changing its value. So I do need, however, to distribute this into both terms in my numerator. So that will become 12xy squared minus this y and this y do divide to 1, so I'm just left with 9x to the 4th. All over, if I multiply this y in, I get 4y cubed. Now it is true that if you put in numbers for x and y into that blue expression, and you put values for x and y into this green expression, it should be equivalent. Okay, so I will continue forward, and now it looks like, well, gosh, what else can I do? There are a few different ways you can go from here. Most people like seeing that they can factor something out of the numerator, so they can factor a 3 out. They can also factor out an x, so that is certainly one road to take. So then I have 4y squared minus 3 would be left, and x cubed, all over 4y cubed. Now, again, it doesn't mean I can immediately do anything, but if I look at the given information, which is sometimes what we forget to use, it tells me that for every y squared I see, that is equivalent to x cubed, or for every x cubed I see, that is equivalent to y squared. So I do have reason, and I'll show you here in a second. Instead of this x cubed, we're going to substitute in y squared. So I will leave this 3x factored out. I get 4y squared minus now 3. And again, instead of that x cubed, we're going to write y squared because those are equivalent. And now hopefully you can see that I can combine like terms. And so 4y squared minus 3y squared is just 1y squared. And then y squared divided by y cubed, I can use my exponent properties. It will leave y to the first in the denominator, so this leaves 3x in the numerator and 4y in the denominator. And I just want you to take a second and reflect back and take a look at what you did. So if I compare this green highlight to the initial yellow highlight of the problem, hopefully you can see that anything that I would need to do looks like it would be easier done on 3x over 4y as compared to what I was given. And all of this was just basic algebra properties and simplifying, but again, don't forget to use any given information that you have. So in our case, it was y squared is equivalent to x cubed. I hope you find this helpful. This will be helpful when you are doing second derivatives in implicit differentiation. Thank you.